we've got a good one for you today. It's alternating series day 2. So we already talked about alternating series, whether they converge or diverge. Now we're going to start talking about error with them and dealing with the remainder. So if a series has terms that are alternating, that's the first step. It's decreasing in magnitude, and then the limit equals 0. Those are the three things. Then the series converges, so it has a sum s. If the sum s is approximated by the nth partial sum, and the error in the approximation are r sub n, which equals absolute value of the sum minus s sub n, will be less than the absolute value of the first omitted or truncated term. So what this really means is that the error is equal to, this notationally, we would use this. Okay, so if it was like the fourth term, n would be 4, which is equal to the sum minus the sum of the series up to that, shouldn't put 4, up to the series up to that point. So if this is 4, then I would do s minus the fourth term, all right? And that's actually going to be less than or equal to, no, just less than the next term. So really, the next term is the big deal here to kind of approximate what the error can be, what the maximum error is. So pretty much, in other words, if three conditions are met, you can approximate the sum of the series by using the nth partial sum, and your error will be bounded by the absolute value of the first truncated term. So this is also known as the upper bound. Okay, so let's actually put this into good use here. So again, these three conditions have to be met before we do anything. All right, so we have two questions here. One is a couple parts here. So we're given the series right here. Approximate the sum of the series using its first 4 terms. So we're going to go ahead and look at its first 4 terms. So S of 4, which is not approximate, this is actually exactly what it is. So the sum of the series is approximately S of 4, which is going to be, well, the first term, if I plug in a 1, I'm going to get, that's an even number, so it's actually going to be 1 over 1 factorial, which is just 1. If I plug in a 2, that'll be negative 1 over 2 factorial, which is just 1 over 2. Plus 3, which is going to turn into, again, that's going to be positive 3 factorial, which is going to be 6. And then it's all, can't tell it's alternating here. 1 over 4 factorial, which is going to be 24. So we add all that stuff up together, we're going to get, this is going to equal, not approximately, this is going to equal 5/8. Okay, so the sum of the first 4 terms is 5/8. Now explain why the estimate value in A differs from the actual value by less than 1 over 100. So first off, we need to state our 3 conditions here. So first off, this is alternating. Before I can talk about anything else, I have to say it's alternating. You can tell by this in magnitude, ignoring the pluses and minuses, this is getting smaller and smaller, so it's decreasing in magnitude. And then the limit and approaches 0 of a sub n, which is just 1 over n factorial. Since it's growing really fast on the bottom, is equal to 0. Those 3 things are met. So now I can say that the error is going to be equal to absolute value of R4, which is going to be the sum minus S sub 4, which is less than the next term, which would be the 5th term. Well, what is the 5th term? So if I were to plug in a 5, I would get positive on the top over 5 factorial. So I would get 1 over 5 factorial, which is equal to 1 over 120. Okay. So my error is less than 1 over 120. All right, which is indeed less than 1 over 100. So this is true. So I just explained why this is true, and that's by the alternating series remainder theorem. Okay. So my error is less than 1 over 120, which is definitely less than 1 over 100. So a lot of times I'll ask you questions like this, and you just need to know what the theorem is. It's really just looking at the next term. So we had to use the results to explain why the sum cannot equal 0.7. So I'm really using this right here. Okay. So I'm going to kind of highlight this. I'm really using this that the sum here. I'll write it like this. Okay, so if this is true, then if I just play around with this just a little bit, then I'm going to say that S sub 4 minus the fifth term is less than the actual sum, which is less than S sub 4 plus the fifth term. So the total sum is in between me taking away the fifth term from my fourth term and adding my fifth term from my fourth term. And my sum is going to lie somewhere in between there. So that's what this little part right here means, if you just play around with it a little bit mathematically. Okay? So what is my S sub 4? My S sub 4 is 5/8. So I'm going to do 5/8 minus my fifth term, which is 1/120. Less than the sum, which is going to be my 5/8 plus my 1/120. So I got some decimals here, so I'm going to get 0.617. So my sum of my series is in between 0.617 and 0.633. There's more decimals there. Okay. So my sum of my series is somewhere between here. So clearly S cannot equal 0.7. There's just no way it's going to happen. Okay. All right, so how many terms are needed to approximate the sum of the series so that the estimate differs by the actual sum by less than 1/100? Justify your answer. So like super similar type of dealings here with what we've been doing with the alternate series remainder theorem. So the series is going to be approximate. We're just going to keep adding over and over each part of the series until I get to a term that's greater than this right here. So absolute value, of course. So I'm not really caring about the pluses and minuses here. So first off, I do have to state that it doesn't matter what order I do this in. I'll just go ahead and find these terms. So the first term, if I plug in a 1, is going to turn into just 1. Minus, I plug in a 2, it's going to turn into a minus. 1/2 to the fourth, which is 16. If I plug in a 3, it's positive. 1/81 minus, this is going to be 4, so 1/256. And I'm going to actually take it right here, and I'm going to stop and chop. Because I finally reached a term that is much larger. Sorry, not much larger. That is smaller than 1/100. The denominator is much larger. Okay? So how many terms are needed? Just 3 terms. That's it. 3 terms are needed, but I can't just say that. I have to make sure that that actually does follow the alternate series remainder theorem. So I do have to say that it is alternating. This is decreasing magnitude. Just look at it, you can tell. And that the limit is 0. Yeah, we can just say that. It's fine. Here. Just do that. Yeah. So, again, this is all that I need here. I'm just going to use 3 terms. Reason is because my error is less than the next term. In this case, if I use 3 terms, my error would be less than the next term, which would be 1/256, which is less than 1/100. So this is why this works right here. So again, we're kind of just getting a little technical with the theorems, but that really is going to wrap it up for the alternating series remainder theorem, which is just our second day of alternating series.